Thank you. Thank you. First of all, I would like to convey my sincere thanks to the organizer for this invitation. So, my presentation will be on the topic application of solid waste materials for adsorptive removal of toxic phenol from wastewater to protect environment and to generate circular economy. So, my name is Ashanendu Mandal. I am basically a person from oil and gas industry. I worked with a premier national oil company called ONGC for more than 34 years. But this particular research is based on my own research performed in the University of Calcutta. So from the presentation's topic itself, a few things are very clear. The important features, for example, it is for the wastewater treatment because it is removing the toxic phenol from wastewater. So it is very much useful as far as to protect the environment is concerned. Secondly, you see, we have utilized solid waste materials as adsorbent. So these waste materials are plentifully available all over the world and almost at zero cost. So this is very advantageous from the economic point of view. Third, also the principle of this separation of phenol from wastewater is through adsorption. So it is a very simple procedure and it does not involve much cost involved for setting up the process. So many small scale industries can prefer to go for this particular way of removal of phenol from wastewater. And finally, you can see that we will see in our presentation also that these waste materials after utilization of wastewater treatment can be utilized fairly disposed as well as can be utilized for brick industry. So it can generate the circular economy. So what I am going to cover here, introduction, objective of the study, materials and methods, results and discussions, and finally conclusions. Phenol, it's basically derivative of benzene. It's soluble in water and acidic in nature. It is colorless, hygroscopic, crystalline substance which turns pink in air owing to its oxidation. Phenol is a very useful material because it is mainly required for the construction purposes, and for that phenol is produced through hydrolysis of chlorobenzene or oxidation of isopropyl benzene. But our concern when phenol is coming as a byproduct from the chemical industries in their wastewater. And you can see what are the quantities of phenol coming from the different industries. For example, refineries, wastewater has got up to 500 ppm. Coal processing industries have got up to 6,800 ppm. Coking industry has got up to 3,900 ppm and petrochemicals 1220 ppm. Other than that also many dye industry, many paints industry and all those leather industry, they also discharge their wastewater in which phenol is present. Besides industrial wastewater, phenol is also available in domestic and agricultural runoff due to the use of insecticides or pesticides. Phenol is categorized as a priority pollutant because of its toxicity, and that toxicity can cause cancers as well as chronic diseases. Phenol also affects badly on soil, plant and groundwater. So there is a allowable limit for safe management of the environment in the surface discharge water as per EPA US as well as per the ministry in India. Up to 1 ppm maximum can be discharged, and if it is above that it has to be removed. And for potable water as prescribed by WHO it is only 0.001 ppm. There are many technology available for removal of phenol. For example, polymerization, electrocoagulation, extraction, filtration, photodecomposition, electrophoton methods, advanced oxidation process, enzymatic degradation, microbial degradation, membrane-based separation, ion exchange, and finally adsorption. So they are physically, chemically, or biologically being utilized in those separation processes. Adsorption, which we have utilized in our research work, it's very cheapest and most popular in recent times. What is adsorption basically? It's a process that occurs when a gas or liquid solute accumulates on the surface of a solid or a liquid adsorbent. So it is basically a surface phenomenon. So during the adsorptions, both physical and chemical activities happen. If it is physical, then it is known as physical adsorption. If it is chemical, it is known as chemical adsorption. And in many of the cases, for example, for all our adsorbents, we have found both physical as well as chemical adsorptions have happened to different degrees of extent. In case of physical adsorption, the forces operating is mainly van der Waals forces. And in case of chemical, it is mainly chemical bonds, maybe a hydrogen-hydrogen bond or pi-pi bonds. The physical adsorption involves very less quantum of heat of adsorption, but chemical needs more. And another important aspect is that physical adsorption is reversible, but chemical adsorption is irreversible. So when we will go for regeneration of the adsorbent after adsorption, this particular scenario or phenomenon is very important. As physical adsorption is reversible, so disruption can take place, and so those adsorbents after regeneration can be reutilized. But if the chemical adsorptions have happened, then it cannot be, because once the chemical reaction has happened through hydrogen bond or pi-pi bond, that cannot be reversed in under any circumstances. So the regeneration efficiency will go down. Now, in our objective of the study, what we will be doing, we have taken 8 adsorbents for investigation of phenol removal, and those 8 adsorbents are categorized in 2 types. One is biological waste. 4 adsorbents are there in this category: guava tree bark, rice husk, neem leaves, and activated carbon from coconut coir. And another category is industrial waste adsorbents. And in this category, we have the adsorbents rice husk ash, red mud, clarified sludge from basic oxygen furnace, and activated alumina. So these are the industrial waste materials. And after preparation of the adsorbents, we will be doing their characterization, because these characterizations are very important to have some idea about the adsorption potential. And these characterizations we will be doing through SEM, XRD, FTIR, BET, and point of zero charge. Then we will be doing the experimental part. In the experimental part, first we have the batch experiments. And in the batch experiments, we will have some process variations. For example, initial pH variation, contact time, adsorbent dose, temperature, and initial phenol concentrations. All these process conditions can be operated very comfortably without any extra arrangement to be done for the adsorption process. And secondly, you will find that these process variations are important to know the maximum potential of adsorption under which optimum conditions it's happening. And after these experiments, we will be doing the modeling. This is very important, and this can basically give us the idea what sort of mechanism will be taking place during the adsorption process. This can be done through kinetically with respect to time variation, isotherm study with respect to the equilibrium conditions variations, and thermodynamic study with respect to the temperature variation. Then we will be doing the predictive analysis also. This is ANN modeling, that is the utilization of artificial neural network modeling. This is very important, and first time we have utilized for adsorption purposes. And so that's why our novelty of this research is mainly because of the use of the adsorbents which have not been tried by others. They are plentifully available at zero cost. And secondly, we will find that this sort of predictive analysis also has been done through the utilization of artificial neural network. Then we will be doing the scale-up design, where we can convert our research process conditions suitably for the industrial applications. We will be talking about the regeneration of adsorbents, how it is made possible. We will be taking the real industrial wastewater also. Initially, when the experiments will be carried out, we will be preparing the phenol solution. But after getting the optimum conditions, we will be taking the industrial wastewater also, and that can be examined whether our process conditions will be utilized comfortably or not. And finally, we will have the safe disposal of the spent adsorbents. Another important thing also we have done, that is the column study. Because many in industry, they will prefer, instead of batch adsorption, they will go for the continuous process. So the column study has been carried out, and in that case, we have taken only the best adsorbent as per studied through our batch study, that is called neem leaves. And here also the process variations will be done to optimize and getting the maximized conditions for maximum removal of phenol. That is the variation of bed height, flow rate, and initial phenol concentration. And the way we have done for the batch process here also in a little different way, but almost all the studies will be carried out like kinetic modeling, isotherm modeling, and we have also a comparison of adsorption capacity with respect to neem leaves as well as with the other adsorbents taken by other researchers. We will be talking about the adsorption mechanism. We will be also having the information of real industrial wastewater treatment under optimum condition, scale up design, regeneration of adsorbents, and here for predictive analysis, we will be doing not only the ANN modeling, we will be doing the conventional multilinear regression method also. Now let us prepare the adsorbents. We'll go very quickly and we will be going, or we'll be basically not showing all the slides because of the time constraint, but the important phenomenon will be discussed very quickly. Like a guava tree bark that will be collected from the guava trees. After washing, we'll be grinding it and we'll be taking the minus 44 plus 52 mesh size. This is rice husk we have collected from a rural area, washed it and grinded. And same mesh size you have taken, that is minus 44 plus 52. And this mesh size practically will be taken for all the adsorbents. Then we have taken the neem leaves. So you can see here, neem leaves have collected from the neem trees. This is the coconut coir, but instead of utilizing the direct coconut coir, we have made the activated carbon by taking after washing it in a furnace and maintaining at 800 degrees centigrade for 1 hour. Then the powder has been utilized as adsorbent. This is rice husk ash we have collected from the rice mill, and then wherever this rice husk will be utilized for small scale industries as a fuel. Then this is red mud will be collected from the aluminum plant where the bauxite is being treated for getting the aluminium. Then this is clarified sludge from basic oxygen furnace. This is mainly from the steel industry. And in there, we will be producing the carbon-rich molten pig into low-carbon steel. There, this sludge is generated that we have taken. And finally, the activated alumina. This is also from the aluminum plant. And this is mainly having aluminum oxide as well as some quantum of silica, ferrous iron oxide and titanium oxide. Now, in case of phenol preparation, that is the adsorbent preparations, we have taken 1 gram of phenol in 1000 milliliter of stock solution, so that 1000 ppm or 1000 milligram per liter is the stock solutions concentration, and that can be diluted as and when required to change our concentration of initial phenol. Then after adsorptions, we will be getting some residual phenol, and if you would like to know what is that quantum, we will be utilizing this way of measuring its absorbance through UV spectrophotometer. Initially, we will be taking some known concentration, and finally, after making the calibration chart with respect to absorbance, we will be evaluating what is the residual phenol after adsorption. And pH is measured through pH meter, and pH variation is done with the addition of sodium hydroxide and hydrochloric acid. So this is the batch study you can see here. First, we have taken in a beaker the phenol solutions. The ppm varies from 5 to 500, and with the addition of sodium hydroxide and HCl, the pH varied from 2 to 12. And whatever quantity of adsorbent dose will be required to go to the equilibrium stage, before that also we will have variations of dose, and for that we will be taking the adsorbent dose measured in a measuring balance. And then this beaker will be placed in a mechanical shaker where time and temperature will be maintained. Temperature will be maintained from 25 to 50 degrees centigrade and time 30 to 600 minutes. And within this time period, we will be seeing that equilibrium has taken place. Then we will filter it, and the filter will be used in a UV spectrophotometer for making its absorbance, and through the calibration chart we will be getting what is the residual phenol concentration after separation of phenol in the adsorption process. And these are the process variations for all the 8 adsorbents. So quickly you can see here all process variations what we have shown in our diagram that has been maintained for all the 8 adsorbents. Then we will be doing two important calculations. One is for the calculation for phenol removal percentage, another for phenol adsorption capacity. In case of basically you see characterization, first we have done the SEM, that is scanning electron microscope. Here the topography picture is available and all are showing a lot of pores in them. So this is good because the surface area also will be more because of the more pores. This is XRD, and XRD is showing some peaks in them. The peaks are basically because of the crystalline nature of the adsorbent. More the peaks, definitely more crystalline it will be, and crystal structure rather than the amorphous structure is better for adsorption. FTR studies also we have done for all the adsorbents. You can see for all adsorbents the figures are there with the variations. The lower peaks are basically related to the functional groups, and based on this you can see here what sort of functional groups are available in all the 8 adsorbents, and these functional groups are important for chemical adsorptions because they are making the either hydrogen bond, pi bond, etc. Then we have done some other physical properties also, like bulk density, effective particle diameter, surface area, and point of zero charge. Surface area we have measured through BET method, and you can see here good surface area in a unit of meter square per gram is there for all the adsorbents. And point of zero charge we have done through the pH drift method by adding sodium nitrate solution. Point of zero charge means at this particular pH, the adsorbent surface is neutral. Then the experimental part is there. So in the experimental study, what we have done basically, with respect to pH variation, when the other things are constant, then if we plot them, the y-axis is the percentage removal of phenol and x-axis is the pH variation. So we will find that there is a single peak, means at one particular pH, the separation of phenol will be maximum. So this is the critical pH, or the you can say the good pH which we can maintain. Then contact time variation. The contact time variation is showing that initially with time the percentage removal will be increasing, but later on it will be almost steady or constant because the equilibrium have taken place. This is adsorbent dose variation. Like time variation, this is also similar. Means if we add adsorbent more and more, the more separation will take place. But after certain time, by adding more adsorbents, basically it will reduce the surface area, exposed surface area, so the adsorptions will get reduced. And temperature variations you can see here, some are increasing and some are decreasing. The increasing means it is endothermic and decreasing means it is exothermic. And if we see the variation of initial phenol concentration with respect to increase of initial phenol concentration, the percentage removal will go down. And this is very important. This is finally at optimum condition, maximum what percentage of phenol will be removed, that is shown here. For guava tree bark, it is 90.67%, rice husk 94.74%, neem leaves 97.5%, coconut coir 95.2%, rice husk 93.3%, red mud 87.5%, clarified sludge 63%, and activated alumina 21.8%. So the maximum removal possible is through neem leaves, which has gone up to 97.5%. Kinetic study, we have done both first order and second order, and we found only red mud has got first order and all others have got second order. First order means it is physical and homogeneous. Second order means it is chemical and heterogeneous. Then these are the kinetic models. Richenberg model we have done, and here we found that adsorption process supports film diffusion. Thick model we have done. You can see here that rate determining step is established through this modeling. Yellowwick model we have done, and it shows that chemical adsorption has taken place. Furuso and Smith model has been done, and it is supporting that phenol moves faster from bulk to solid stage. Boyd model, it is for chemical adsorption. Then we have done the isotherm models, Langmuir, Frenlu, Temkin, and Deer. And we find that maximum cases, the Frenlu's isotherm model is valid. Langmuir is only for Rice's gas and Deer for basic oxygen furnace sludge. And this is very important because we will be calculating our quantum of adsorbent by utilizing the best model of isotherm. Thermodynamic study we have done for del G, that is gives free energy, entropy and enthalpy, and we can getting the information of adsorption mechanism through whether it is spontaneous or not, endothermic or exothermic, and random or not. ANN study, as I said, this is very unique for adsorption we have done for the first time, and we have got total 813 data. Both LM and SCG model has been taken, and we have done the transfer functions through hyperbolic tangent and sigmoid also. And total data, we have segregated 70% for training, 20% for cross validation, and 10% for checking. And after that, when we will be doing the checking, we can find that through this model as well as through the experimental data, if we compare, it is more or less same. Scale-up study, now we will be rapidly closing up. Scale-up design, we can calculate what is the quantity of adsorbent will be required. Regeneration we have done through the utilization of distilled water as well as 30% of ethanol solutions, and up to 2 cycles the regenerated adsorbent can be utilized, as chemical adsorption has taken place almost for all the adsorbents, adsorption process. So after 2 cycles the potential will go down. Real industrial wastewater also we have compared, and we find more or less they are similar under optimum condition. Safe disposal, this is very important. Here you can see that if we heat or incinerate the adsorbent after adsorption of phenol up to 800 degrees centigrade or above 800 degrees centigrade, the toxicity will go down. So we can safely take them into the brick industry where the temperature is being maintained at 1000 degrees centigrade, and along with other ingredients it can be utilized for brick manufacturing. So it can generate the circular economy. In the column study, we have taken only with the neem leaves, and here the setup is there. It is basically a continuous process. So in the column, we have taken the adsorbent, and from this bucket, we have pumped the phenol solution in them, and then the filtrate is evaluated for remaining phenol concentration. We have done the bedhead variation, flow rate, and phenolic concentration variation, as well as pH variations. pH and room temperature are 3 and 30. Then the breakthrough curves have been drawn, and these are the experimental results. We have done the kinetic model for a column study also, Boat-Adam model, Thomas, Ian-Nelson model, Olborska model, Ianid model, and modified dose response. And we find that Ianid model is the best suited, so that has been taken for the scale-up design. Column isotherm study for Langmuir and isotherm both have been studied. The adsorption capacity, you will find that neem leaves have got 23.7 to 48.1 adsorption capacity, and this is more or less good as well as better in comparison with many other materials. And in the mechanism, you can see both physical as well as chemical adsorption have taken place. Then this is with the real industrial wastewater. The scale-up study, as I said, the quantum of adsorbents of, that means neem leaves, how much will be required for separation of wastewater phenol in them can be calculated. And regeneration also we have done same way. Basically, it is like base study. And for column study, we have done the multiple linear regression method also for prediction analysis. And this is also very good. ANN also we have done, and that is also very good. So finally, if we are to conclude that we have taken 8 adsorbents, 4 are from biological waste, 4 are from industrial waste, and those adsorbents all are very effective for separation of phenol. And another important thing is that as they are very cheap and plentifully available all over the world, so that can be really utilized for especially for small scale industry where the expenses will be very less. And secondly, as I said, it safely that can be disposed also, and finally that can be utilized for brick industry also. It can generate the circular economy. So these are the papers. That's all. Thank you. Thanks a lot.